going to hopefully just give you a general idea about what biomedical engineering is, and I'm going to talk more specifically about injury biomechanics, which is what I study. So to tell you a little bit about myself, I did my undergraduate degree in mechanical engineering, and I did it out at Queen's University in Kingston, Ontario. And so within the mechanical engineering field, I specialized in biomechanics and kind of the biomedical option of that. When I completed my undergrad, I came out here to UBC to start my master's in biomedical engineering, and that's what I'm working on now. So what is biomedical engineering? It turns out that this is kind of a hard question to answer because biomedical engineering is an extremely broad field. So what I work on as a mechanical engineer in biomedical engineering is very different from what someone in an electrical engineering discipline would work on as a biomedical engineer. But kind of the Google definition of biomedical engineering is that it's the application of engineering principles for healthcare purposes. And this usually has to do with biomedical device design. So almost any medical device you can dream up has been made by biomedical engineers. So lots of you probably know people who have had hip replacements or knee replacements. And in those surgeries, we basically replace a part of the bone with an implant, and that implant is something that's developed by biomedical engineers. So that's what you see in the top left-hand corner there is a knee replacement, and that would be designed by biomed engineers. Similarly, fracture fixation devices, so implantable screws and plates, are designed by biomed engineers. Prosthetics is a big part of the field, and it used to be very much a mechanical specialty, but now is kind of evolving into these wearable robotics, and because of that, now it's becoming more of an electrical and mechatronics problem, but it's still all under the blanket of biomed engineering. And I mean, there's just 150 other things that I could tell you about. So pacemakers, surgical robots, any kind of imaging modality, so CT scans or MRIs, that's all kind of within biomedical engineering. So just keep in mind that what I tell you today is only a really small part of this far broader field. So in terms of what is the difference between biomedical engineering and medicine, doctors tend to diagnose and prescribe and treat patients, whereas we as biomedical engineers develop the devices that they use to accomplish that. So we kind of develop solutions for problems that surgeons or other doctors might have. So that means that there's often a collaboration between the two fields, and a really good example of this is I've been part of a program called Engineers and Scrubs at UBC for the last 2 years, and this program basically facilitates collaboration between engineers and doctors. So at the beginning of the year, we'll bring in a number of doctors, and they present a whole series of problems to us. And from those problems, we choose 3 or 4 maybe to work on, and our students then develop a medical device to suit that need throughout the year. So I just wanted to kind of demonstrate that biomedical engineering and medicine are not in these isolated silos. They are very much or interact with one another, and physicians, I guess, are kind of on the front lines with the patients, and as biomedical engineers, we tend to be in the background making the devices that they use. So the kinds of jobs that we hold often will be for medical device companies and building these devices. And then there's also another large component of jobs which are just within pure research, and I'll talk a bit about that later. So does anybody have any questions before I move on? Okay, so now I'm going to talk a little bit more about what I specialize in, which is biomechanics. And so like biomedical this is just now the application of mechanical engineering principles to help us understand the human body. And so often this can involve gait analysis. So looking at how people walk, we can see the joint angles that people move through as they go through their gait cycle. We can look at the loads that maybe occur on the joints throughout walking, and then we can compare that to a non-healthy individual or healthy walking to non-healthy walking, and identify patterns that will help us diagnose problems or perhaps make corrective devices to make someone's gait more healthy. So that's one component of it. And what I work on is injury biomechanics. So again, we're applying the laws of physics to the human body, but now we're looking at how does the human body fail, what causes injury, and what are the loads that occur on the body to cause injury, basically. So I'm sure a lot of you are probably taking physics right now, and you're looking at kinematics, and so motion and forces and dynamics, and we apply all of that to the human body as a system. And so this image on the screen shows in a frontal accident, an occupant in a car would be seated, and they might undergo this kind of whiplash action. And so what we would want to know is how does that motion cause reaction forces in the body, and in what ways can those forces cause injury to the occupant. And so when we talk about mechanical failure, we're interested in two kinds of failure. One is structural failure and one is functional failure. So structural failure occurs when the loads applied to the body exceed the injury tolerance of some structure. So we can do experiments on, say, cadaveric specimens to determine what loads perhaps the tibia can sustain. And once we know what loads they can sustain, then we could calculate on, in a scenario like this, what are the loads that would be on the body in practice. And if those loads are greater than the injury tolerance of the tibia, then you would get fracture. This is what we consider to be structural failure, is this breaking or tearing of one of the structures within the body. And then functional failure is a little bit different. It's not as easily observable visually, but basically when a load applied to the body can cause disruption of some function, then that's what we consider a functional failure. So in concussive injuries, then a lot of these are caused by rotation of the brain rather than impact of the brain, and that can cause stretching of the neuronal fibers, and that stretching is what might cause injury rather than an actual physical tearing of that structure. So these are just a couple of the different things that we tend to look at, but overall, like the underlying concept in all of this is that all responses in biomechanical systems are governed by the laws of physics, and we apply the laws of physics to understand what's happening in these injury scenarios. So I guess one of the big questions is, what are the applications of injury biomechanics? And it turns out that the automotive industry is actually where a lot of this research and development is taking place. So all car companies need to subject their vehicles to crash tests to determine if a vehicle is safe for an occupant. And of course we can't put real people inside these vehicles, so we have to use crash test dummies. And crash test dummies are a lot more sophisticated than you might originally think. So they don't just need to match the mass and shape of an average human, but they also need to match the joint response of a typical human. So if a the dummy experiences load that would cause whiplash, the neck needs to go through the same motions that a human neck would in one of these impacts. And so the development of these crash test dummies is one big application of injury biomechanics research, because we want to make the response of these dummies as close to the human response as possible. And then basically any injury prevention device is all biomedical, biomechanical stuff. So development of airbags and seatbelts to prevent injury. Beyond that, you can go into safety equipment and sports equipment. So not just helmets and padding, but also the development of skis and downhill mountain bikes can all be done within biomedical and biomechanical engineering. And then these are things that all tend to occur in industry, and then human tissue research is more what takes place in the research field in universities like at UBC and like what I do. And this is where we start to look at the tolerance of the human body to different loads. So we use cadaveric specimens to understand what loads that different parts of the body can sustain. And then last of all is consulting, and this is where we can get into kind of forensic analyses. So we can look at the human body and injuries that were caused in an accident, and based on those injuries come up with probable scenarios in which injuries occurred. So those injuries become our evidence, whereas in other fields it would be mechanical evidence, or that's not related to the body. And that again is a job that occurs within industry. Questions? Okay, so as I said, I'm